if you hear the term green AutoML, what does this mean to you? And now I want to stretch your brain a little bit. So I would like you to think of a term which you immediately connect to when you hear green AutoML. Just think for yourself for a minute. Listen to your gut feeling maybe. All right, everyone got a keyword, term, whatsoever, a thought? Okay, this is gonna be interactive now. No worries, no wrong answers. So what did you connect with green AutoML? You're not sure. Okay, that's also a valid answer to this. What about you? Weight sharing? Yeah. Yeah. Saving resources, yeah, by integrating brilliant tricks to save computational resources in particular. So what about you? You looked very mindful in between. Efficient hardware, yeah. Efficient hardware is also a very important point. Maybe in the back with a white shirt. Yeah.
General fishing libraries, for example, some advantages just more efficient than others.
Yeah, very good. So we have a big range, so various topics already covered. And I hope that also for the rest, I can convince you that green AutoML is actually also for our community an important topic to think about and to be respected also in future works. And not only to consider it as a limitation, but maybe also as a chance in order to drive innovation. So I asked GenAI, so in particular ChatGPT, what it thinks about what green AutoML is like, and it's a lot of blah blah, but the most important part here is that it has a strong emphasis on minimizing the environmental impact. And this is not so far from being true, yeah? So it already captures the idea of being more green quite well. Then I also asked it how it would look like in terms of the picture. And then we can also see by Dolly a couple of thoughts here. So we have nature included. We have renewable energy. So the energy source also seems to matter in some sense. Yeah? We have performances here that go quite steep. Okay, could hint at efficiency. Then there are some keywords, but I think those are mostly attributed to AutoML to be captured in that picture. But as you can see, the color green had also quite some impact, but not only the notion what we as humans are being somewhat already branded towards sustainability, understand them under the term of green. All right, so why is that even important? Well, we heard already a lot about LLMs and these huge models with vast amount of parameters, and these models consume really a huge portion of energy. And there has been a report on GPT-3 training, which consumed more than 1,000 megawatt hours. First of all, 1,000 does not seem to be so much, but who of you knows what your yearly energy bill is like? So how many watt hours do you consume? You don't know. So I can tell you mine. So my girlfriend and me, we are consuming around 1,000 kilowatt hours to 1,500 kilowatt hours. So it's really a magnitude of order higher to just get one model. And if you then calculate this into the consumption, into the energy consumption of the electric car, with 20 kilowatt hours, so you can even drive a Tesla, which consumes a little bit more kilowatt hours per 100 kilometers than more efficient cars. You can drive more than 100 times around the world. Yeah? And then for inference, so calculating with like 10 million queries per day, which is not too far off. So they have around 100 million active users per week right now. So the energy consumption we use up for inference with GPT-3 was back then 260 megawatt hours. First of all, this sounds like, yeah, inference is again cheaper, but if you just deploy this model for 5 days, you already exceed the training costs. And we are always complaining about the expansiveness of training GPT models, but the inference cost is way higher. And this did not get better. So GPT-4 just increased in size, and voila, we consume even more energy. So if we just follow this road into this rabbit hole, then we will end up consuming a lot and a lot and a lot of energy in the near future already. So now you can say, well, yeah, these are these big tech companies, and I'm just a small person in the big world, and I'm maybe just a PhD student, postdoc, professor running a chair of a couple of people. I'm not part of this big play or big game here, so my consumption is relatively smallish. Might be smaller, but it matters. And to just incentivize you to think about what energy consumption you have with your work, I would just be honest with you and tell you what I consumed with my team. And this was quite shocking to me, at least. So when we wrote this paper Marius talked about in the announcement, we just looked at our HPC report after a year and looked at how many CPU hours we consumed. And it turned out that with a small team of 5 AutoML researchers, we consumed an equivalent of 1 million CPU hours per person, which ended up to be published in a couple of papers. But if you just look at how much energy this costed and how many trees we would need to plant to compensate for that carbon footprint we really were responsible for, this was quite shocking to me. So we would basically need to plant an entire forest of 3,600 trees. And these trees would need to survive for 10 years to suck up all the CO2 we emitted with our experimentation. And then you must not burn them, yeah? So if you burn them again, the CO2 is up in the air again. You can turn them into furniture, yeah, that's fine, but in general, you need to keep these kind of resources that you try to put in place in order to compensate for your emissions. And also we already, within 1 year, could have driven 18 times around the world. And I mean, this was also then in addition to traveling to conferences, which has also quite an impact. And this is only an estimate for our chair. So if you scale this up to the entire machine learning community, I mean, this might be 6 to 8 papers here. If you look at conferences, which are oftentimes doing also computational experiments, and you have like 1,000 papers, 2,000 papers being accepted at top-tier conferences, but around 12,000 were submitted, you can easily scale this number up and try to get an image of what is there. All right, then when starting to talk about this kind of topic, I often ran into the argument, but wait, AutoML is naturally striving for improving or increasing efficiency, and that's just the natural way of how AutoML develops. It's true, yeah. So we are working mostly on some benchmarks where we have fixed constraints like number of CPU cores, memory allocation, which you can have. We limit the runtime, like you must not exceed 4 hours of total runtime. We have a set of data sets, objective functions, and in order to become state of the art, what you need to do is to become faster or better. So either you want to have a steeper curve, which immediately goes down and you have high efficiency, so you get to your target quite quickly, or in the end, you at least want to become the best in order to have the best performing model in the end. But higher efficiency is somewhat a relative concept. So is better anytime performance what we are naturally striving for in AutoML really better energy efficiency? So again, some interactivity to not lose you. And we make it a binary classification problem now. So everybody just needs to predict now whether it's yes or no. So is better anytime performance equal to better energy efficiency? Show of hands. Okay, then I can stop here. Presentation is over. I already convinced you. Perfect. So efficiency already differs if you just swap the time variable you are looking at. So what you are often looking at in AutoML is runtime, but in black box optimization, for example, a very prominent criterion is samples, so number of black box function evaluations. And what you can see here is basically that you have the same 3 runs, but just now for different x-axis. So previously we had runtime, where run 2, the orange line dominated all the other curves. Here we have number of samples. So we just look at how at what point was the evaluation function triggered and how did performance improve over that. And here we see now that run 1 with the blue curve dominates. So just the swap of the images. It's the same runs, but different outcome. And if you put this now for energy consumption, you can get a third image, because if you just look at methods which might be slow and you have not a good sampling efficiency, but a good energy efficiency, you can end up with a better outcome in this regard. So efficiency really depends on the context. So it's a relative concept. And this is important to keep in mind. And what we would like to give as a return for the user might also depend on what's then the relative context we are heading for. So what is now green and what not? We have looked at green AutoML to be maybe implemented at different levels. So at the level 0 for all these models, we could have some resource awareness so that we know at least how much energy has been consumed or whether we use the resources effectively. On level 1, we could integrate that knowledge and strive for more resource-aware strategies for AutoML. So searching for machine learning models in an energy-efficient way. On level 2, we would like to go even beyond and not only make one AutoML process efficient, but maybe also use the information, the knowledge we've gathered, we've collected already for other AutoML runs, and also transfer it to new AutoML runs, to not just waste these resources. So what is oftentimes done is you simply forget about everything you did before. But this is valuable information. You have invested energy in order to get to this information. Why not make it usable and sustainable? Okay, no, I don't want to update. Thank you. So how can you do that? Well, first of all, you can focus on algorithm design. So you can try to design these AutoML systems to be greener and integrate with green thinking. And I would really encourage you to do that. And I will also later on show you an example, a success story, so to say, where green thinking really helps to improve state of the art, not only with respect to consumed resources, but also the anytime performance we are naturally striving for in AutoML. And I would just like to ask you to embrace this as a shift of perspective and really thinking about the problems in a different way. And maybe this will result in a way of thinking that helps basically and is a win-win. And then in turn, once we have AutoML shiny and running quite nicely, we could also use those kind of tools in sustainability problems. So trying to make the world a better place, help reducing carbon footprint at other places where it's not so easy to do, but AutoML might help. Another thing is benchmarking, which is natural to us because all the AutoML literature is mostly empirical. So what you basically do there in order to demonstrate that the method you're proposing is beneficial or somewhat useful, you will do some experimentation. But here it's also crucial to do the right experiments, yeah, and be mindful about how you design your experiments in a way that you can really observe the outcomes you're interested in, but also not wasting resources on the way. And sometimes you just run your experiments and nobody can reproduce them anymore. That's one issue, but this is then also wasted resources because if you cannot reuse those experimentation data, it's only computed once, and the next people who would like to compare with your approach would basically need to recompute everything, which then stack up over time. The more the baselines grow, the more energy consumption you will have in benchmarking. And the first way to get a greener thinking to life is maybe to, first of all, just being transparent about this, raising awareness that all this costs energy and all this has an impact on our planet on which we are living. And also this gives, if you are transparent and just report the numbers of the carbon footprint you emitted or you had for your experimentation, will make other people think. Probably they won't ignore it the first time, the second time they read it in papers, but if this becomes a more common thing, then people also will start to process this information and asking themselves questions. Why do they report it? Is it really important or not? And how do I compare in this regard? And we already did that, basically. So we created a checklist for the AutoML conference, which was luckily or fortunately also integrated into the submission system. So you're really asked to be transparent about your resources you consumed for your experiments and what carbon footprint you produce. So now, of course, the question comes how to capture energy efficiency at all. Yeah? How do we measure this? And then you could say, well, it's so simple. Hello? It's very easy. You just plug in a measurement device and you just record at the power plug how much energy you consume. Problem is that most of the time we as researchers do not have access to these systems. Yeah? So if you run your experiments on HPC hardware, which is standing somewhere in a compute center, you must not go there. So they don't want to have you there plugging your devices into their plugs. This is not going to happen. And then it's also not so easy to measure even at the power plug itself, because you also have other factors being involved. So there's a cooling facility in the compute center, which also consumes energy. And when you do computations, you will produce heat naturally. And this heat needs to be cooled down again. And all this are factors which you can't even measure at the power plug. So we somehow need proxies for this, for these kind of measurements. And how to do this properly is still an open question. So if you're interested in working on that, you can do so. Maybe some machine learning could help here. What has been proposed in the past is that you basically assume and pose the assumption that the longer your algorithm runs, the more energy you will consume. That's true. So there's nothing wrong about it. Energy consumption is an cumulative function which will just consume more. You cannot give energy back by doing more computations, right? However, if you compare different algorithms to each other, they can use resources in various loads. So it's not that easily comparable. So just because one algorithm ran longer than the other one doesn't mean that this algorithm will also consume more energy. And this really depends then on the workload. So here we have again the runs from before. And if you still remember, this run here was the energy efficient one. And here you have basically the orange line here, which consumes the most energy and really goes up high. But in terms of samples, they ran all at the same time. And in terms of runtime, this compares also quite easily. So at this point, all the algorithms had the same runtime, but consume different amounts of energy, quite drastically. So having all this now in mind, we can try to tackle this problem by a first surrogate. So what you know about hardware is thermal design power. This is a value which tells you how much your hardware is supposed to consume at most, at full workload. And then there were some nice people which just recently published a paper here and proposed this formulation, just multiplying the TDP with the workload integrated over time. So you basically have a share over time, how much consumption you had in terms of your full workload, and then you just multiply it by TDP, and then that's it. The thing is, this is not really correct. So it will drastically over-approximate your energy consumption and assumes that your energy consumption scales linearly with the workload, which is not true. So when you look at these graphs here, so on the left graph on this side, you see the clock frequency of a CPU compared to its energy draw. And what you see here is an exponential curve. So the higher the workload, the more energy you will consume. Meaning, scaling this linearly will drastically over-approximate your energy consumption. Penalizing algorithms which might only use small workloads on a CPU, and these are actually the ones you're interested in. You have the same picture for GPUs, of course. So also there, the higher the workload, the more energy you will consume, but not linearly, but rather sort of exponentially. So what to do about this? Well, actually, you would need to factor in this function, this behavior of the workload, but has not been done. So this is a very recent paper. I think it was published like a month ago or something. So here also in open space, quite a low-hanging fruit to do it in the right way and not just assuming linearity where it's not the case. All right, so why do we not come up with the right ideas in the right place? Well, it's mainly because all these kind of measurements are highly underreported in the literature. So just try to grab on, take a, hold on some papers in machine learning literature and try to find the numbers, how much resource consumption there was. If you're lucky, CPU years, CPU hours are communicated, but most of the time you will only be told, I use that CPU architecture, this RAM load, and that's it. But you don't know how much exhausted these resources have been. So what we try to tackle here with this work, MetaCure, is to first of all assemble a meta-learning data set where we record all these resources. So the colleague Raphael Fischer here really sat there on his workplace and recorded the energy draw of different hardware setups, ranging from a small energy efficient ARM board up to a really well-functioning and proper workstation. And what you can see here is basically that the energy draw also really highly depends on the type of hardware you use. So here, for example, you have logistic regression as a learning algorithm. And on the left-hand side, you have logistic regression being trained on a very energy efficient board. On the right-hand side, you have logistic regression on a end-user computer workstation. And you get the same model. It has the same accuracy, but the energy draw is completely different. So what you could do here now is basically also to optimize these different types of objectives simultaneously, going for energy draw and performance, generalization performance. And this is what we already started to tackle here. So we put a meta-learning approach into place and really ask before we train the model on which hardware to do this, and then also trading off the energy consumption trading off the energy consumption against the performance in order to get a good trade-off, which is then predefined by the user. And we are lucky to have Daphne today to also tell you more about multi-objective optimization with respect to green AutoML. So there will be another session on that. Yeah.
Maybe just first of all, this equation looks like usually stays the same, which makes sense, but for HGV, it somehow changes. It usually even as a variable. Why that?
Yeah, this can also be because your hardware is working in a different way, that you have different cache sizes internally, and your algorithms then sometimes behave differently. Yeah, yeah. So also a factor you might want to consider. I mean, we already know this from the algorithm configuration literature, that you also want to tune your algorithm to the hardware you have in place because it might perform differently. To be honest, I would have not expected to have large differences in performance, in generalization performance, but yeah. All right. Good. So what else can we do about it? Well, we can just look at the issues we have in AutoML systems. Yeah? And AutoML systems are these trial and error sampling approaches most of the time, which just blindly try different parameterizations, different compositions of pipelines, and then observe their performance value and try to incorporate that kind of knowledge into further decisions, and also trying to incorporate that knowledge in order to get to the best solution the fastest. However, sometimes it might happen that these algorithm combinations are incompatible, that you have misparameterizations, that you choose parameter values that do not work together, or you have data properties that do not suit the needs of an algorithm. And what might happen is that you just compose a machine learning pipeline consisting of various steps, and at some point, this machine learning pipeline will crash. Because you, for example, need to have only numerical values, but no categoricals, and you did not do any categorical encoding, it will crash. So what happens, basically? Well, all the computation you invested already to compute this pipeline so far is wasted, because all you will observe is not working. Yeah. And what Nguyen and et al. Did here in 2020 is basically to fit a meta model to predict whether a pipeline will crash or not. And with this, they already could save some resources, yeah, and thereby also prevent this waste of resources to even happen in between, which also improved a little bit optimization performance for AutoML, but not too much. So what we did, more or less simultaneously, so this was published in 2021, but was already on the way for quite some time because it's a journal paper. We just thought, well, if you have AutoML systems, and AutoML systems work typically with an internal timeout, yeah, so you don't want to look at a single machine learning pipeline for days if you only have 4 hours set by the user to find a good model. Yeah. You impose an internal timeout to cancel evaluations prematurely if you do not expect them to give you a result in a reasonable amount of time. So what is bad about this? Well, it turns out that for some AutoML runs, you just waste 60 or 70% of your runtime, of your overall runtime, in timeouts. And timeouts were basically the same as the crashes, so you just observe the timeout, but not the performance value, which helps you finding a better model. So what we proposed here is basically a kind of safeguard that predicts us the runtime for machine learning pipeline, and then we can decide whether we want to risk it or not. And if it says timeout, for example, we just drop it, we never evaluate it. If it says no timeout, we will hand it over to the evaluation routine, run a cross-validation or Monte Carlo cross-validation whatsoever. And then, of course, it can still happen that the timeout occurs because it's a machine learning model. It can do mistakes, yeah? So might naturally happen. However, what is cool is that in some cases, we can do up to 400% more successful evaluations. So it actually works. Yeah? And we can even spend up to 200% more time on these successful evaluations. So we can really reduce the wasted time on time-outed evaluations by just incorporating such a safeguard. So what's the problem with such a safeguard? So, yeah, Leonard? Yeah, true, but I can tell you that these predictions are quite precise for the settings we have observed, so it's not too bad. So we let that run on our system and it all performs well. So we did this on an Xeon E5 2670. What do you use? Yeah. Do you use an i7 and an i9? Well, you use different resources. And those CPUs become faster over time, so runtime predictions will vary. So we collected a lot of data for building the safeguard on our system and used it also on our system, and it works. However, transferring this to another system is again a problem. And guess what? We ran into this problem. So we collected all this nice data, so it's tons of data, really in the size of gigabytes, just runtime measurements. And then our compute center in Paderborn decided to get a new HPC computer because the old one was really outdated and they wanted to get rid of it. Okay, we have 6 generations later CPUs compared to the data we collected. And it makes a difference, definitely. So what do you need to do? Well, you need to have some grounding routine or some transfer routine in the first place and really adapt your data to your hardware, which is not an easy problem. So for our case, it was lucky. So we collected CPU data and transferred it to another CPU from the same manufacturer. So it had roughly the same command set. But it was really not easy to do. What you do is basically you sample different anchor points in your data set, observe the runtime on your new system, and then try to scale the runtimes you have in your data to refit your safeguard model. However, if you now want to also use heterogeneous hardware, and there's plenty nowadays, like GPUs, FPGAs, neuromorphic chips, and some energy efficient boards, just like we use in this Meteor study, you have an issue. So runtime highly varies, and now you need to collect a lot of data. So here are definitely very huge construction size if you want to use such mechanisms in the field where you really want to exploit different types of hardware and use that to your advantage for increasing sustainability. What else can you do? Well, we have already heard about it, multi-fidelity optimization. So multi-fidelity optimization also is a resource allocation scheme, basically, and you only want to put resources there where you actually are expecting promising solutions to be. So how does this help maybe also to prevent timeouts? Well, if we don't have a meta model, which is difficult to build, we can also use these low fidelity evaluations here to have a sneak peek on the full runtime behavior and try to extrapolate how much runtime it will need also on larger budget portions. And then you can really do also quite easily stuff for which you don't even need to have a model. You just need to have some algorithm which then observes the runtime behavior and extrapolates this to further budget steps. And this basically you can also easily integrate then in such evaluation schemes. What else? So auto-stopping might be a good idea. So why spend more resources if you're already done and you have a good solution? Maybe it's not worth it to really squeeze out the last bit of performance. And it could also happen that there is not even a hope that you can improve. And there are various methods already in the literature where you can have, for example, AutoML integrated into random forests, for example, to just build a forest up to a certain number of trees, which is good enough to give you the more or less the best possible performance with in terms of the number of the trees, or which also won the Best Paper Award at the AutoML conference in 2022, was an auto-stopping criterion for Bayesian optimization. So if your uncertainty remaining in the surrogate model is mostly aleatoric uncertainty because of the noise in the evaluations and the cross-validation faults, then you can also stop. So there's no point in optimizing aleatoric uncertainty. You cannot get rid of it anyway. And maybe as a first mean, most of the approaches are quite complicated to implement. So as a first mean, you could also just make use of a very simple trick, which has been already used in various communities for some time, that you incorporate a criterion when to stop if you don't observe any improvements anymore. Of course, you run at the risk that you might miss the optimum, and you could have found, after a couple more iterations, a new best model, but how much hope is there? And such mechanisms you can then include in order to put this all into an AutoML system, and I just did that. So what I really use here is multi-fidelity evaluations, observing the runtime, doing auto-stopping, and voila, we could basically come up with a new approach for automating multi-label classification, which is really fast and very good. So what you can see here in the top plot is the runtime we need to give comparable results. And what you see here is basically a speed up factor of 5. So we reduced the runtime by a factor of 5. And could give out comparable results within 2 hours, for which the fastest baseline almost needed 11 hours. And on average, a single baseline would need between 14 or 15 hours. And this runtime is not only a single CPU, this is 8 CPU cores in parallel. So what you save there in terms of resources is quite a lot. So I told you this naive timeout prevention scheme where you just observe basically how much time you need on lower fidelities and then not try those which would exceed your time thresholds on higher fidelities. How well does this work? Well, if you look at this chart here, so this was really just this naive timeout prevention scheme, you can reduce the number of time or the fraction of timeouts you run into quite drastically. So here you have only 2% of the times, 2% of the time ending up in the timeout. And for other state-of-the-art optimizers, you're around 50% up to 70% even. So why is that even cooler, except for the fraction? Well, the fraction for the other optimizers is even more in terms of total compute time, because here we mostly only use like 2 hours. So we have an auto-stopping criterion terminating our approach, and that's it. So this is really a result which just occurred because of thinking about how can we just spare resources? How can we just make the optimization process or design the optimization process in a way that we get along with as few resources as possible and trying to prevent any waste of resources. And as I said to you in the very beginning, I really would like to ask you to embrace this idea of making these algorithms greener and try to leverage this as an inspiration for making approaches more efficient in any way. So reducing energy consumption, reducing a runtime, and having still competitive performance to other more complicated approaches. All right, so that you believe me that this really works well, on the y-axis here we have the mean regret. So the distance from our current solution to the best ever found solution, and this then averaged over all the data sets and seeds we have observed. And this line here is this very simple approach which just incorporates green thinking. And here you can really see that even after 4 hours, this wins in this competition by quite some distance. All right. Good. So what to do with saved resources? Yeah? I think I already implicitly said it for the previous slide, so you can just spare it. Yeah? Don't use it. If your model is already good enough, then what's the point in trying to improve it? But if you can effectively improve your results, then it's also useful and reasonable to do so. But you can also use these free resources in order to invest time, compute into reasoning about things. Yeah? So if you manage to spare resources on the ground level where you do not waste resources anymore for evaluating machine learning pipelines, you can use these resources to maybe reason about how well do different methods perform, how much resources do they consume, and try to anticipate this stuff, which also again needs compute to reason about it, and use it for these kind of things. So in contrast to just predicting the next suitable candidate for evaluation, you might incorporate more compute into reasoning about that. And maybe you can even then extend the scope of your pipeline. Yeah? So we have also already spoken about explainability stuff. Yeah? So that you really want to have additional features for your end user to be provided. And if you free resources for this model search, you might also reinvest these resources in order to come up with explanations already or whatsoever. So let's talk about benchmarking. So one thing I learned during my time as a PhD is to stop computing things over and over again. So whenever I wrote an AutoML paper, I just reran all the baselines. And I needed to do so because my data I stored was not sustainably stored. Yeah? Either parts of it got lost, it was badly documented, I didn't know anymore what I wrote where. And of course, this is bad scientific practice, but also from an economical or ecological perspective, this is also quite bad to just recompute everything. And here I would really like to give a big shout out to cool libraries which you can use in order to have better benchmarking, which is consistent with community standards and also facilitate your research. So on the left-hand side, for example, you can see AutoML, which is, by the way, integrated in carbs you have already learned about. And what is cool about it is that you no longer need to evaluate machine learning algorithm configurations on the data sets in order to develop your HPO algorithms or AutoML algorithms, but instead, you just query a surrogate model predicting the performance. And these surrogate models have been built on vast amount of data. And yes, this is expensive in the first place, but the more you use it, the more energy efficient it becomes. And these models have shown to be quite accurate in terms of estimating the performances. So you can really trust in them and develop approaches with respect to them and really come up with good ideas here. And what is cool about it is that it also goes faster. So when you do the real executions on your benchmark data sets, it takes time. So for example, I carried out a huge computational study comprising 84 CPU years of compute. Took like 2 months to get all these results on an HPC cluster. And here you can just use these kind of surrogate benchmarks and get results within seconds. So just to give you an idea, I just recently published a paper using AutoML, and I conducted 10,000 HPO runs on a single machine in a single day. So this is nothing you can do or afford on scale as a researcher with your HPC centers, but here with these kind of surrogate benchmarks, you really have a chance to speed up your research quite drastically. And then you have also cool libs like NUSLib here, which also incorporates such surrogate benchmarks for developing neural architecture search algorithms. So I would really like to ask you to rely on these kind of benchmarks, look at what is currently best practice in the benchmarking scene for AutoML, and use these kind of benchmarks, A, to help them being more sustainable, B, to save your resources and make our field in general greener. So having all these resources and consumption ideas now in mind, it's not only about energy you consume, but also what energy you consume. We, for example, here in Germany, have a quite bad mix of coal energy included in our energy mix. So this coal energy will produce a higher carbon footprint. However, many HPC centers already really rely and really enforce renewable energies and only have energy contracts signed with renewable energy providers. Now you could go ahead and say, well, if it's renewable, it doesn't produce carbon and carbon emissions, and then I'm completely free to do whatever I want and can waste all the resources. But that's not true. Whatever energy you consume is bad energy. And whatever energy you consume is missing at another place and could be used for different things. And therefore, if you can spare energy, should not stop you from doing research, but should motivate you to really think about energy you want to consume or invest. And cool idea, but also very complicated idea is smart scheduling. So really schedule your experiments in times of a day where energy is there, where it's plenty and cannot be used anyway. So for example, in Paderborn, I know this figure, 150% of the energy production stems from renewable energies, so by windmills. And the city is not big enough to use up all the energy, but it can also not be transported to other places. So the energy is really stuck there. So they could even produce probably more than that, but you cannot use it. And if you go to such places, if you're residing in Germany, for your PhD, you can even apply for compute resources in Paderborn at the PC Square. You can make use of such factors. But of course, it's highly intransparent and you cannot really go for it. But this would also be a big challenge in our field or in computer science in general to allow for such mechanisms that we can use energy whenever it's there and spare energy when it's basically impacting the world more. So coming to the end of my talk, I want to equip you with some take-home messages. And the first thing is to really be mindful. Don't get lost in reiterating thinking, but at least try to think about what is your impact and try to think about what is the cost of your experiments before you do them at scale. Run small batches of experiments in order to find maybe bugs which only occur in the wild if you really scale up a little bit rather than just having a single execution on your local machine. It's really a pity if you already ran 20 CPU years of experimentation just to notice that there was a bug somewhere and you need to rerun everything again. It costs time and it costs a lot of energy, and there are certain mechanisms just like scaling up step by step, which you can easily incorporate, which make your life easier and which also helps to spare resources. Be curious and transparent. So really don't feel like this green thinking is limiting you in your research or whatsoever. Try to use this as an evolutionary selection pressure to come up with approaches that really go beyond the state of the art in any way. And just help in reporting, being transparent about your energy consumption to raise awareness, to motivate others to also communicate that. There will always be people who do not want to communicate that. And we should also not start shaming people for using resources. Using resources is always also a context-dependent concept, and it's sometimes very hard to measure the value of some experiments for the social impact. And yeah, in case you cannot measure it properly, which is most often the case, try to at least estimate it. And there are really nice online tools already available. Just search for it, carbon footprint, CPU, online tool, and you will end up on websites where you can even choose the type of CPU you're using, plug in numbers, how much compute you used, so how much computational time, and it will give you estimates of your carbon footprint, of your used energy, and also give you some nice figures of how often could you fly between New York City and London or whatsoever. So in order to also give you a feeling of how much it was. And just a shameless self-advertisement again. So if you just use PyExperimenter for designing your experiments, it already measures or tries to estimate your carbon footprint while conducting the experiments. So in the end, it's just grabbing data from the table, which is anyway stored, and aggregating this data. And then as a last point, be creative. Yeah? Yeah, still rather consider it a chance or a driver for innovation. So these are my references, and of course I'm happy to have a very nice new team where I can work with. So please follow us also on social media stuff, and yeah, I'm happy to further on discuss with you now and trying to answer your questions, whatever you have on mind regarding green AutoML or green AI in general. Thank you.